So good evening. The title of the lecture today is referring to one of the jobs that I have. I have two jobs. One is I'm a scientist, and that's the title, and I study fire. And it becomes an intimate relationship where I do and see fire from the beginning, and I see how fire spreads, and I see how fire ends, or how it's suppressed, and what it has emitted in the meantime. So I want to share with you a little bit of the secrets that I have learned. We have learned is a plural effort that we have learned about fire. The other part of my job that is not in the title, but is in the lecture and in my professional spirit, is that I am an engineer. So everything that I learn from fire is not just fascinating by itself, and I want to share it with you and with other people, is that we want to use that knowledge for the good of society, and that's the engineering part of my job. So I will start telling you how I got into fire. I was doing my PhD at the University of California at Berkeley. It was very warm there. And I was studying how to make a space flight safer for astronauts. The spacecraft, no matter where they're going, they're maybe just orbiting, they're going to the moon, they're going maybe to Mars in the future. The astronaut has to be breathing oxygen. The space industry loves polymers, plastics, because they're very low weight. And they're very versatile and they're very strong, which means that a spacecraft naturally have a lot of polymers. And oxygen and polymers already mean that you have a flammable atmosphere. In the space, you cannot call the fire service. Or maybe the astronaut is the fire service himself or herself. And the evacuation routes are very limited. And suppression has intended consequences if it gets into the electronics. So the stand of space agencies around the world with fire is absolute zero tolerance to any kind of fire event in space. And that is very nice, and we can help them a lot, but in space you don't have gravity. Just that detail, the lack of gravity, completely changes the behavior of fires. This is an image that you have on the top that was done by NASA, it's very famous. This is a candle in space and a candle here on Earth. You know how candles on Earth are. They're going upwards because of buoyancy caused by gravity. The smoke is hot air, is less dense, so it weighs less, and then it goes upwards, it's displaced by the surrounding air. And a candle in space has no preferred direction. It doesn't want to go upwards more than it wants to go sideways. It means that the smoke actually displaces the oxygen itself, and the oxygen cannot get to the candle as fast as it can do on Earth, because the smoke is pushing it actually away. It means actually candles are less flammable in space, or polymers are less flammable in space than they are on Earth. But there is another type of fire that is not in the candle, which is smouldering combustion. It doesn't have a flame. You have experience with this, everybody has experience with this, it's barbecues, it's embers burning in your fireplace, or cigarettes. And those fires really like smoldering, the absence of gravity. So I was asked by NASA to take a look at this and to develop knowledge so NASA could apply this into safer spacecraft in the future. So I'll tell you, that was how I got into this, and now I can tell you the things that I learned. What is fire science, for example? Fire science is a field of a discipline, it's a discipline of science that actually tries to create new knowledge about fire, how fire starts, how fire spreads, what fire emits, or what are the consequences thermally or chemically, and how fire ends and how it can be suppressed. And that's the part of the knowledge that fire science creates to control an unwanted combustion. And then we pass this knowledge, or we expose this knowledge to the engineers and to the authorities. And hopefully, we cross our fingers, that the authorities and the engineers will pick up this knowledge, will learn this knowledge, and then they will combine it with previous knowledge that they had, or previous devices or previous technologies, and they will combine them in a way that something new comes up. Something new that is safer, is better, is better designed, and that is the process of innovation out of new knowledge that is created. And that is the end of fire science. But all this happened a long time ago. This happened about 1.5 million years ago, where our ancestors were tired of running away from wildfires, and little by little, over the course probably of decades, of hundreds of years, stopped running away from wildfires and actually started to be intrigued, probably play at the beginning, and they went back to the fire and started to play with it. And over the course of hundreds of years, thousands of years, we humans as a species, we end up controlling fire. Not only just bringing it back to our settlements, but actually being able to initiate it at will. And that led to what is considered officially the single greatest discovery of humankind. It led to a different way of cooking, and it changed our physiognomy and our ability to different activities. It changed the way where we can live. We moved into different latitudes because we could heat up the environment. It meant that we actually were not at the mercy of sunlight to see. It meant that we actually could control light and bring light in, at times or places where light was not existing. It meant to different kind of warfare, different type of hunting, and it actually led to the process of changing materials, metallurgy, and chemical processes, and it led to, later on, to manufacturing, to steam engines, to the Industrial Revolution, and to the modern world. And that is by the process of controlling combustion. But sometimes combustion is not controlled or is not wanted, it's unwanted. And this is captured really well in this saying from Finland, Finnish saying, that it says that fire is a good servant, but it's a bad master. And the same field that created the scientific and the technology, the science and the technology of how to control fire and come up with this light that we have today and most of the transport that made you to here today and manufacturing most of the elements that are around us. The same scientific field is actually providing solutions to this threat, this ancient threat of fire that has been always facing society. And in the future, it will continue facing society. And even if we go into space, it actually chases us because the way humans are and the planet is, it means that flammability will always be there. So this is the definition that I gave you before of what is fire science, of creating this knowledge that hopefully will go to with engineers. And I will tell you why it is important. It's important for many reasons. I've already alluded to this. One is that we humans did not invented fire. We discovered fire. Nature, as an entity, invented fire. And it actually has a very positive role on the planet. Extremely positive role in the planet. In the news, you always get the negative role of it because it's a threat to people that might be living close to the forest that is burning or might be affected by the pollution, or maybe a really bad fire actually can really have negative consequences on the ecosystem. But we don't talk much about the good fires that, for example, close the carbon cycle. Without the fires, then nature would not have the ability to close the carbon cycle. The same carbon cycle that we humans are now perturbing if it's closed actually naturally through fire. Or the oxygen cycle. It's very nice to always have a concentration of 23% in mass of oxygen in the air. But who keeps that magical number at 0.23? Why is not higher or lower, and why does it vary in different locations at the sea level? And that is because wildfires actually close the oxygen cycle. And without wildfires, the planet will not be able to actually bring that number to be steady and so in a value that we all like tremendously. So that's important. But when fire happens in a building, that is really bad news. Obviously now in London, in the UK, we will all be thinking of the tragic events of Grenfell that happened a year and a half ago. But in our job, we are constantly reminded of horrible fires that happened in the past, and they are happening as we speak, and preparing ourselves for the ones that might happen in the future. If you look historically in the number of fatalities that fire has caused, you go to 2 countries. There is only 2 countries on the planet Earth that have decent data, historical data on fire death. This is the US and the UK. And the rest of the world they have some good data one year and not good data the next, or they cannot go back more than 10 or 15 years. So if you go into the US, that's the plot that I'm showing you over there. This is the number of fire fatalities in the US as a function of time. And you can see that 100 years ago, the fatalities were tremendously, they were actually 10 times, almost even more than 10 times higher. So over the last century, we have reduced the number of fatalities by 90%. That is a success story. Many, many things have been done by society and by professionals to explain this clear downward trend. But that has a price. It has a cost. The fact that, for example, that we have to protect citizens from fire means that the way we build buildings is different. That could be considered a cost. It's a good cost. It's an investment, if you want, investment in life. But it means that you have to call special engineers, and the special engineers have to bring they have to modify the design of the building to make sure that actually the building is safe. That, in a way, is a tag associated to fire. Also, we have fire service. Any town, not maybe village or little hamlet, but every town on the planet has a fire brigade, far or close. You don't have tsunami brigades, you don't have earthquake brigades, you don't have even flood brigades, but you do have on the planet fire brigades. And that tells you the omnipresence of the fire threat. It also tells you the amount of investment, of resources that are put into protecting people from fire. So that's one way of investing or protecting yourself from fire. This as a tag associated to this. The other one is, and this is particularly strong in countries of high income, like the UK and the US, and most of continental Europe. But other countries, low income, medium income, they don't have the ability to invest into how the buildings are designed or in the fire service. They pay the price in the number of fatalities that the fire causes, which is a very high, or the number of buildings that disappear, or the number of businesses that are stopped just because of fire. So we humans have the ability to choose where we put the money, but we always put the money to associate fire, to put it far away from us or to put it close to us, so to speak. Yes, in the UK, for example, we're talking about from 7 to 10 billion between indirect and direct costs of fire, which is significant. It's about a third, actually, of the budget of the country in education, which is probably one of the most important and less controversial budgets of the country. And to see that a fraction of it actually goes into protecting us from fire shows you that we are talking about something that is quite important. If you look into the number of fatalities because of injury-related events, not because of natural causes, not because of sicknesses, but because there has been an injury, fire represents 5% of the worldwide death related to an injury. You can compare that to war, which is also injury-related, and it causes 2%. So in terms of how this is affecting the planet, the numbers speak by themselves. When engineers want to protect citizens from fire in a building, they can do many, many things. Some of you might be familiar with some of the things that they can do. Some of you will be familiar with the others. So I want to just try to wrap up and give you a common, an integrated view of your different experiences. There are at least 6 layers involved in the protection of a building. Not all 6 layers have to be present. The engineer hopefully has, or they have, considered all the layers. At some point, it has taken a decision. Not all layers are equally effective. Not all layers are equally popular in the culture of the country. The first layer, no controversy, the single most important layer that could exist, prevent the fire. Do not let the fire happen. And this is not just as simple as don't light the cigarette at home. I'm talking about the science of preventing the fire, which is making sure that something as flammable as polymers. We are all right now surrounded by polymers. We humans love polymers, and all of them are flammable. But they have levels of flammabilities. We also believe we humans are fantastic ignition sources, not ourselves. But we are surrounded by ignition sources, the electricity, the heating devices, the electronic devices, the lithium-ion batteries. And you don't want the ignition sources of a certain size to meet materials of a certain flammability. The combination of the two is pretty bad. So that is actually what the science and technology of prevention looks into. If we have failed in this layer, prevention has failed, there is a fire, then you trigger the other layers. The first one is you should detect as soon as possible. And there has been a breakthrough technology about 40 to 50 years ago, which are smoke detectors. And we have always here one when I gave a lecture with us. This is a very inexpensive technology. It was a breakthrough, continues being a breakthrough. It saves so many lives every single day on the planet that is just overwhelming. It should definitely get a Nobel Prize. The smoke detector, or the creator of the smoke detector should get a Nobel Prize. And you should detect as soon as possible. And then what you do with that information is part of the layer. You tell this to the people who are in the room, hopefully yes. You tell this to the people who are in the floor of origin. You tell this to the whole people in the building, in the campus. That's to be discussed. That's what is the alarm and how you communicate it. But you have to first detect it. The second layer is what do you do with that information you have detected. So now what? The third layer kicks in, evacuation. People should be put away from harm as soon as possible. And this is something that is not, I mean, the pathways and the routes for evacuation are designed by engineers, but the people who interact with the pathways are sociology agents, are people, and that they behave in a different way, not in a way that we can fully understand with our Navier-Stokes equations. So that's what actually, this is a layer where sociologists have a lot to say in how to design our buildings. It's not just us with engineers with our mathematical models. And you want the evacuation to happen as swiftly and as safe as possible. In this campus, in this room, that's a really easy, relatively speaking, case, how to evacuate. If you are in a high-rise building, or in a hospital, or in a prison, these are the three most difficult evacuation scenarios that an engineer can face in their life. And the taller the building, the bigger the hospital, or the more people in the prison, the problem complicates enormously. The fourth one is a layer that is very important, culturally speaking, in the UK, and you all know this, is the compartmentation. And this is what explains, we don't have anyone here today, the little blue tags that we have in the UK that says fire door, keep closed. And we have many of these doors, right? Like just exiting this room, for example, you have so many doors. We are used to this, but when a visitor comes from the US, they think it's funny. Like, how many doors do I have to open to get into the room that I want? In the US, we only have one door, right? To keep the wind out or the sound out. And this is something very important. It's a passive type of protection, is that if there is going to be a fire in a room, at least the fire and the smoke should not be entering different rooms and then complicate further the problem. So you compartmentalize. It's actually a military way of mind. It says, I identify a problem. I want the problem to stay there while I'm trying to address it. The other one is suppression, fifth layer suppression. You should attempt to suppress because you have a sprinkler, which is something that Europe doesn't do much, but the US does a lot. The US, they don't have much fire doors or compartmentation. They have a little bit, but they have a lot of sprinklers everywhere, and you can see that. And they're very good at doing sprinklers. But that's an active type of protection. It's one of the layers. In the UK, we use the other layer more, the compartmentation, although there is a little bit of suppression. Also, if the fire service has arrived, that fire service helps in evacuation, the third layer. The fire service helps in the suppression, okay, the fifth layer as well. And it can actually help in the last layer of all, which is structural resilience, which is the building where the fire is happening, where people might be inside or in the vicinity, should not collapse while still people are in danger. It's much easier if it will never collapse, but sometimes engineers are allowed to let the building collapse. But the question is, it should be collapsing when there is no one inside. And then the question that engineers face is, how do I know when people have left my building? That communicates to the third layer, evacuation, right? And all these layers have different abilities, they call for different engineering disciplines, call for different bits of science, and they are present in all buildings on the planet. Even if you go to places where the safety culture might be weaker or historically not present, they still consider these layers. They might just go for one, they might not complete the layer, but all the layers are considered by engineers. So now that I've hopefully told you what fire science is and how we use it and how important it is to communicate this to make the environment safer, I want to tell you things that my group and I together, we have been doing for the last 15 years that have been academic in the country. So 4 topics, I'll go a little bit fast, and some of them are bigger than the others. The first one is safer polymers. The fact that we humans are addicted to plastic is, I'm a mechanical engineer, so I really try not to put this as a negative thing. My wife thinks it's negative, but we mechanical engineers, we adore plastics, we love polymers. They are wonder materials. They can do the things that we have been dreaming to do as engineers until they were invented. But they have 2 problems. One will be recycling and the damage to the environment. The other problem that I want to tell you about is that all polymers are flammable. Literally, there is not one polymer invented by nature, like wood, or by humans, synthetic polymers, that is not flammable. It's just a discussion of how flammable they are. Some of them are not very flammable, but they are still flammable. They can still burn. Some of them are incredibly flammable, so flammable that you would not be allowed to put it legally next to a person. They are actually scarily flammable. And then is the area in between, right? And we discussed it. So we help the industry, the polymer industry, to understand the flammability of what they're doing and then to control it. How do they control the flammability of what they're doing? That is actually called, maybe if the polymer base has been fixed, is flame retardancy. Is what can I do to the polymer that I really want to put into this product for this particular technology for electronics, for example, that is still safe, but it can actually do their job. And that is actually something that engineers can do. And then they have to prove the authorities that it's not just their opinion, that actually this polymer really is safe. And there is a set of standards of simple tests that they can do to prove the authorities or to anyone that asks that truly that polymer that is going into these products can actually pass the safety test. There are many different ones. There are like literally hundreds of tests depending on the application, depending on the type of polymer. But all of them are trying to interrogate what is the behavior of this polymer when it's exposed to an ignition source or to a fire. And if there is a rank, and if it's very high, it's very flammable, it's not legal. If it's very low in the rank, then actually it might be allowed in some countries or in others. So I want to show you this video. It's a video that we took in the lab. It's a very simple experiment. We are burning a polymer strip. It's just about 10 centimeters long. We bring a bouncer burner to the tip of the polymer, and it's exactly the same polymer. I'm not allowed to tell you which polymer it is, but one of them has been treated chemically with magic powders. Literally, it's magic powder. It's a tiny little bit of magic powders, and it completely changes its fire chemistry. And one of them cannot be ignited, and it will be considered by all standards that use this test as totally safe, almost inert. It has not done anything. Whereas the other one, that doesn't have the magic powders, is catastrophic. It actually fails by all possible views that you could think. It ignites, it spreads, it produces black smoke, and it drips. I mean, it's literally it's a horrendous one. And the other one doesn't ignite, doesn't spread, doesn't produce smoke, and it doesn't drip. And it's a slow motion video you can see. And the question is how you go from one material to the other? How can you cause such a big behavior change? And all of it, I'm a mechanical engineer, so we explain that in terms of heat transfer. So this plot over here, you have time in seconds, and here you have the temperature of the surface of your polymer upon being exposed to the bouncer burner, which is really hot. So what happens is you have the black curve. The temperature of the surface starts to increase. Obviously it's hot, the bouncer burner is hot, the polymer gets hot in time. There is a point, a moment, where actually it is so hot that it starts to decompose. A polymer decomposes, the hydrocarbon chains, the long chains, interlink of the polymer start to break down and start to produce off gases, which don't smell good whatsoever. That's not fire yet, that's what is called pyrolysis. Those gases that are coming out, those gases are flammable. Those gases are what causes the fire itself and will feed into the flame. So you need the process of pyrolysis to actually create a flame. It's a previous step to actually the proper burning, pyrolysis. And if you wait a little bit longer, that pyrolysis will form the flame. What we can do from the point of view of heat transfer is you can manipulate the thermal properties of the polymer, hopefully not making it weaker, more heavier, or more brittle, or you hopefully don't want to change all the good things of the polymer, and you modify the heat transfer in a way like the red curve, where you delay the onset of pyrolysis and you delay the onset of the flame. Maybe you actually delay the onset of the flame so much that the flame will never appear, or maybe the pyrolysis will be kept at a very long time, or actually will happen in very small amounts. And that is something that you can do changing the heat transfer. You can also change the chemistry, which is what flame retardants typically do, these magic powders, and end up with an equivalent to the green curve. I'm a mechanical engineer, so I prefer to explain flammability in terms of heat transfer. If I were to be a chemist, which I'm not, I will be explaining today flammability in terms of the chemistry of it. The thing is that the two of us, the heat transfer and the chemistry, have to be present to understand flammability and flame retardancy of polymers. When you look into all the processes that really have happened in the process of pyrolysis, the heating and the onset of pyrolysis and the flame is fascinating. I have devoted a significant amount of my life to explain and to understand and to quantify and to combine all the processes of chemistry, of heat transfer, radiation, convection, conduction, cracking, charring, oxidations, heterogeneous oxidations, etc. Absolutely fascinating. And this is one of the things that we've been doing. And we start at a small scale in the lab with the computer, We try to simulate the experiments in the lab, and then we feed this information to the engineers that live in the real life so they can use our knowledge at the larger scale into the future. So this is actually feeding one of my dreams. It has continuously been a dream, and I'm working hard of my dream, which is that there is chemistry on one side, for you, chemistry on one side, and there is a heat transfer on the other one. It's a physics phenomena. And the lower we are at the scale, the smaller are the scales, the more fundamental is the research. But hopefully, I'm an engineer, okay? I don't forget where we are going. We're going to the upscale of the process, where the actual citizens are being threatened by fire, and we try to combine the chemistry and the physics in a way that actually is truly understanding fire. If I were to live only in one of these branches, I would not be able to claim that I'm working at the top. Obviously, I will choose this branch, heat transfer, because it's the one that I understand the best. But I do an effort to actually incorporate chemistry. We make that effort. And actually, if I were to live very far at the bottom, it will be very fundamental. I might be considered for a Nobel Prize, but it will be very difficult for me to keep track of where really, truly I am going. As an engineer, we're always looking upwards to the citizen and to the real world, which means that we don't get the Nobel Prize for other reasons. So things that we've been doing over the years, thanks to our sponsors, and they believe in us, believing in our research, and hopefully having benefit from our research, is we've come out with novel retardancy methods, which are based on heat transfer. I'm unable to come up with redundancy on chemistry, but we've come out actually with new methods of conduction retardancy, or convection retardancy, or radiation retardancy. We've actually developed composites which are as tough or as light as they want to be in applications for airplanes and trains and cars, but they are less flammable, which has always been hindering composite technology for example, in trains or airplanes, that they were beautifully strong, beautifully light, but so flammable, no country on earth will allow that airplane to have that material. And it was the combination of finding a polymer that is not just strong and light, but it's also not flammable. And that we've been able to work with engineers to do that. And the last thing is we've actually working on to understand the material that we've been burning for the last 1.5 million years, wood. You will not believe how little we know about how wood burns. It begs belief when I have to explain this to citizens like you. We know very, very little. And it has been observed so many times. So now architects have decided that the dream of this decade, a beautiful dream, is the one tall timber. They don't just want chalets or small houses in the forest made of wood. They want tall timbers, high-res buildings. The most difficult type of building to design safely for an engineer. And wood is flammable. And wood, here in the UK, fed the Great Fire of London. So that discussion that is happening, fascinating with the engineer great minds and the architect great minds and the authorities there in the middle, is something that is happening as we speak. And we are trying to help in this discussion to happen, creating knowledge of how truly wood burns. Because if the engineer truly understands how wood burns, the engineer truly can actually calculate a building that is perfectly safe, made of timber, and has to convince the authorities that, therefore, the dream of the architect can come to fruition and be safe. And this is something that is ongoing. Another thing that I want to tell you is related to wildfires. These are not the wildfires that you've been seeing in the TV in California, now happening in Australia as we speak, or I'm from Spain, or in Spain every single year. These are actually a different ones. They only are in TV every 3 years on average. These are forest fires happening in Southeast Asia mostly. Also, they happen in Siberia. They happen in the northern, in Canada. It's peat fires. So most of you probably would know what peat is because the UK has peat. In Spain, we have very little peat, so I didn't know what peat was. So peat, when it burns, it doesn't burn with a flame. It actually burns smoldering without a flame. The fires that I told you that NASA was concerned about, they also happen on the planet. And actually, they lead to the largest fires on Earth. The largest fires on Earth are not the ones that we saw in TV with, unfortunately, beautiful flames. They're actually the ones that don't have a flame. They produce an incredible amount of smoke, so much that the cameras go inside and they don't see anything. And they are reported only when the size that they take choke the whole fraction of the island of Borneo, or maybe they actually impair visibility in Singapore. When these fires are taken into account, they are equivalent in the carbon that they are releasing from actually peat is how nature stores carbon. So when they burn, actually we are destroying how nature stores the carbon to balance the carbon cycle. It's about 15% equivalent. These fires are equivalent to about 15% of emissions by humans, the anthropogenic ones. For an engineer, this is very dramatic because the ones that we produce by humans, at least they benefit society. They are pretty bad. We're going to reduce them, but at least they're actually given power, electricity, comfort, etc. But a source of carbon that doesn't benefit society nor nature, because it's not a natural phenomenon, is something that we definitely, everybody will agree that we can work and reduce and make it small. The way these fires look, these are the ones that you're familiar with. They're flaming fires, the bright flames with black smoke. It's very buoyant smoke because it's very hot, so it actually goes very quickly upwards, and actually so fast that actually it might actually go into a higher atmosphere and be carried from the winds very far away. These fires are very fast. They're a threat to safety. You have to take people away from the fires. That's the main task of the fire service. And this is the other fires, the ones that we worry about, the smoldering ones. You don't see a flame. The smoke is whitish. It doesn't have soot. It doesn't have big particles. It has liquid particles instead. It actually has not burned the vegetation on the surface. It actually has made a massive hole on the ground. And it has made this hole in the ground over the course of weeks, and if not months. It's a process that is very slow. You're all familiar with the smoldering, but it's actually really difficult to suppress. Only nature knows, and the Americans, diverting rivers, know how to suppress a peat fire, which means that in the total life of the fire, these fires they produce thousands of tons of carbon which could be at 10,000, could be 1,000 or 10,000 years old, stored by nature. So this is what happens when the smoke ends up in Singapore. Some of you might be seeing in Singapore. This is a beautiful on the top image of Singapore as it typically is, with very little pollution from cars or from nearby ships. It's a relatively clean city. And at the bottom you have when they are under the cloud of the fires happening in Indonesia or Malaysia. Indonesia has nothing to, well, in principle, doesn't have a direct link to these fires, but the cloud is so massive. This cloud that doesn't go up into the sky actually stays attached to the ground because it's not buoyant. It actually moves into the city of Singapore. It might stay there for weeks, if not months. If you calculate actually the effect that this has in the people of Singapore or the people of nearby towns, doctors typically worry a lot about the components in the smoke. But the number one thing that they worry about, if you ask them to just worry about one type of particle, they will say is the 2.5 PM. It means that it's particle matter, little particles of liquid or solid, which are 2.5 microns in size. They are so small that we breathe them in, they go into the bloodstream, they might actually go into our brains. They are so tiny. It's literally ridiculous and scary. This is the amount of particle matter in Singapore when they are under the cloud of haze produced by smoldering. And here at the blue, you have what typically Singapore would have on a normal day, which is clean, just because of their own sources of pollution, which they have a few, 10 times larger. When Singapore or any country is under a haze cloud, kids, the first warning of the government is the kids should not go into the street, elderly people should not go into the street, and athletes should not be exercised in the open. And actually the badness of the problem and the means how Singapore can fight this actually are very limited. And the consequences, the whole of Southeast Asia, we're talking about the order of thousands, 100,000 fatalities or excess fatalities when the cloud appears. We're talking about a very important traffic route for airplanes and for shipping and land movement, and they lose visibility and actually start to impair the trade connections, and they actually have an economic cost in their presence of these clouds. So what we do in my group is we have a small lab at Imperial here, right? Very small, but if we were to sell it, we can buy a castle in Edinburgh. So we do small scale experiments. Okay, we don't forget that we are trying to solve or help mitigate absolutely massive, the largest fires on Earth. What we do is we develop really good small experiments. Then we develop really good state-of-the-art computer models. We make sure that the computer model is able to replicate fully in detail and is validated the smallest scale. And then we use the mathematics and of the computer to upscale the results to the large scale. And then we talk to authorities, to the fire service, to the engineers, and hopefully they will, with this new knowledge that we create, they will combine it with a previous knowledge, with previous devices, and come up with new technologies. We also, as engineers, we were brave about this. We've been working with ecologists a lot. Ecologists do what is called field trips. So they don't do experiments, they don't have labs. They actually go into the field and they observe the real phenomena. So by working with ecologists so often, I became envy of having field trips, and I think they became envy of having experiments. So we end up together doing field experiments. We went into Sumatra, one of the big islands in Indonesia. We were given by the government of Indonesia a peatland, and we literally started to burn in controlled manner, from ignition to spread to emissions to suppression. For the course of 2 weeks, we were actually doing this, something that we have never done before, not just us. No one has ever done a field experiment. You either do an experiment in the lab or you do a field observation. But bringing the two of them together is what happens when you put an engineer and an ecologist to talk about what could we do next year. And the video that I showed you, I'm going to try to show it to you again. It was fascinating because, for example, we set these fires. It was for the good, no worry. It was not too bad. It was, I mean, they were the biggest fires ever done in science, but they were the size of this room. But we observed these fires during the day, during the night. Typically, scientists go to sleep at night. It means no one had ever observed a peat fire at night. We actually stay there while it was raining. Typically, if it's raining, people actually leave, and they say, oh, the tropical rain, which is like this downpour, has put the fire off. It's an assumption. Did you go back to check? We actually stayed there. There were 2 downpours, massive. They actually collapsed our tent. And the smoldering fires were actually going. Some of them actually accelerated because of the heat transfer process of the rain. So these fires are extremely stubborn. Rightly so, are very difficult to suppress. So before leaving, going back to London, so we have to suppress these fires. So I'm joking. It was part of the experiment. It took us 2 days, and we knew perfectly where the fires were. We could detect them with infrared. With our thermocouples, we knew we had ignited them. We have nearby a lake. We have all the water we wanted. It took 2 days, about 5 people, to suppress these fires. Are extremely stubborn. No wonder that Indonesia is struggling to fight these fires, because if we detect them when they're already going, pretty much there is nothing you can do. As I said before, unless in the US, they actually can divert rivers, and they reflood the land. But that's a very strange case. I think the New Zealand repeated last year once with a tiny little fire. Most of other people, you have a peat fire, you have to suffer it more than actually truly suppress it. This is not, if it was to be, it's not just that it's a massive amount of carbon that is produced in peat fires and that this carbon is ancient. Is that ecologists and atmospheric scientists are saying that an excess of carbon emissions are actually leading to climate change. Climate change is actually leading to warmer temperatures. And then if the soil, and the red arrows are things that we do ourselves. Blue arrows are what the literature is telling us. If peat is warmer and peat is drier, I can tell you already, I can quantify how much you are increasing the probability of an ignition and the size of the fire. If more peats are burning because of climate change, they're actually emitting more of ancient carbon, which actually further produces more carbon. And it creates a positive feedback mechanism, which if it's not disturbed, it will actually accelerate climate change. And this positive feedback mechanism is actually not typically considered by atmospheric modelists. It's a novel positive mechanism, which cannot be tackled because there is very little science. It's pretty much about 5 groups in the world, us being one of them, and us getting together and talking to the citizens to actually create more research in the topic. So now, shorter 2 things, which are typically what I don't present in academic settings, but today, because this is a merge between academic setting and a citizen setting, that I actually can allow myself to explain these things. First one is this unbiased, this fantastic piece of work that we did, which is crazy. I've been spending 15 years of my life understanding how a smoldering combustion starts, how it spreads, and how it's stopped. And it's always to avoid it happening, right? Because we don't want these fires from happening. But I thought one day, I'm an engineer, and the people next to me are doing combustion engines. They're actually promoting fire they're promoting combustion for the good of humanity, to give them power and mechanisms. It's like, what's good about smoldering that society can benefit from it? There are not many of them, but there are a few. And one of them that I realized is the Falklands. Since I grew up, I've been fascinated by the Falklands. And the Falklands, the Argentinians put a lot of mine there. And we have, the UK has maps of where the mines are, but they put this very nasty mine, actually. It's the SB33. You have it here, blown up. It's very small, it's anti-personnel, it's aiming people, and it's made of plastic. So the most robust technology that we have to detect mines actually doesn't work at all with these types of mines. It can be detected by other means, but immediately the efficiency of these means, the speed and the cost and the risk, they're always more negative. And then I realized, but a fraction of these mines, about a third of them, are in peat, because the Falklands has a lot of peat. Can smoldering fires help detect these mines? So obviously I went to the Ministry of Defense, and I told them about my fantastic idea that I can help them detect and demine a third of the mines in the Falklands. And they replied saying, that's a crazy idea. It's very dangerous. Fire is very dangerous. And I thought, no, it was a very civilized conversation. I thought, this is why it's very dangerous to tell an academic not to do something, right? Because then we immediately go and we do it. So I thought, this letter from the Ministry of Defense is the hypothesis of my research. I'm going to test this hypothesis. The Ministry of Defense thinks it's crazy, it will not work, and it's dangerous. So let's see. I'm going to test the hypothesis. And we did the work. We actually, in the lab, okay? The idea is that you have mines. We did this with different mines. We didn't use real mines, don't worry. We used dummy mines, the ones that don't explode, but thermally speaking and size-wise are identical. We use plastic mines and metal mines. We also discovered that in the former Yugoslavia, they also have peatlands with mines, so we thought, well, maybe we can help more than one country at once. And the idea is you initiate a smoldering fire, and then the smoldering fire propagates very slowly, and earth reveals the mine to the person that is looking at it. You can further, not just visually, you can actually use infrared, because thermally speaking, the mine behaves completely different than a rock, etc. And we did this in the lab, and this is what you see. This was the mine. We cover it with peat, and then we ignite, and the fire starts to press. And actually what you have at the end is the mine is revealed to you. Then we actually check what was the damage to the mine, and there was a little bit of thermal damage to the mine, but not enough to actually trigger the primary charge or the secondary charge. So actually, it would not actually make the mine dangerous. And even if it were to trigger the mine, mining experts say that that's not bad itself, that a fire itself ignites the mine. So we published a paper. We were super proud of it. We even showed that it can tell you, the technology can tell you the difference between a rock or a root that is buried and a mine. And we published it. And I think the Ministry of Defense is taking a second look at the work, because we test the hypothesis and we answer scientifically to what we thought of them. So that's one positive use. Not being used yet in the Falklands, but it's public knowledge now. And one day I will be surprised. Someone will give me a call and will say that they have used it in the field. Another role of smoldering, which is not positive, and it doesn't really help per se into a safer environment, is actually something that is going into history, which is the role of smoldering and the Titanic. So you know about the Titanic. You probably know about the Titanic more than I do. And you know that it sank and it didn't go well. Something that you might not know is that the Titanic, and this is not controversial. This is literally not controversial whatsoever. The Titanic was on fire. It was on fire when it sank. It was on fire over the whole voyage. Okay, and it is just a matter of saying when really the fire started. It started 5 days before sinking, or actually started 4 weeks before sinking, because it had a smoldering fire in the coal bunker. And actually, during the whole course, there was a team of about 10 people fighting the fire. The way they fought the fire was they took the coal out of the bunker that was burning and put it into the boilers, because the coal was very valuable to the Titanic. It didn't have much excess coal, so it could not let the fire consume the coal. It might not actually make it to New York. So the captain said, get as much coal as possible out of that bunker, because otherwise we will not make it to New York. This rational response to the fire is actually the only rational explanation of why the Titanic was going so fast when the captain knew perfectly well that it was an iceberg field. and you are not supposed to, apparently, to go that fast in an iceberg field. And no one has been able to give a rational explanation to that decision by the captain, except that the captain was racing the fire in the consumption of the coal. Are we going to make it to New York or not? What it is not free of controversy, and it's actually a role that we had, is that when you actually look where the fire was happening, you see it was happening here. This is the coal bunker. It was actually, the coal bunker is absolutely massive. It's like a whole building made of coal. Okay? So the one where the fire was happening, in the middle was one of these steel plates, very thick. So they're called watertight bulkheads. They're really thick steel plates. They're very specific. This actually is a technology. It was a breakthrough technology of marine engineering that Titanic was the first one to have. This was meant to make the Titanic unsinkable, these watertight bulkheads. They had many of them. You can see how it's split here in this drawing of the Titanic. And they used to stop after several meters. And these watertight compartments allow the Titanic to have damage in the hull, water rushing in, but actually the water not spreading over the whole of the ship, just staying in these compartments. And the Titanic was able to maintain stability with up to 5 compartments being flooded. 6, very controversial, and it was not part of the calculation. So if you see the damage from the iceberg is in white, 1 compartment damage, 1 compartment damage, 3, 4, 5 compartments. The iceberg hit 5 compartments. It flooded 5 compartments. But the ship was meant to stay afloat. And the ship stayed afloat, I think, for about 45 minutes. And then something happened, has not been explained scientifically by anyone, is this mysterious event. Something happened, and very quickly the ship went from engines off and evacuating and waiting for someone to rescue it to suddenly sinking under the floor of the sea. And what happened is the failure of that bulkhead. That bulkhead over there, okay, is the difference between 5 compartments and 6 compartments. So there is evidence that when this compartment was flooded, because this bulkhead failed, that's what actually led to the sinking. And that is the bulkhead that had been exposed to really high temperatures of the smoldering fire that was happening against it. So when we look into how coal smolders, this is something that we do in the lab, we see that the peak temperature is in the order of 1,000 Celsius. When you see how steel being next to a source of very high temperature of up to 1,000 temperatures, it means the steel can easily get to 500 Celsius, maybe 600, maybe peak temperature of 700 Celsius. And then you talk to metallurgists, and you see that all properties of steel deteriorate really rapidly when it reaches those temperatures. So we actually did computer simulations of how the steel will have lost mechanical properties and how it will have respond to the heating. And we saw computer analysis that actually will deform. It will deform in a very funny way. Actually, it deforms first going inwards and then going upwards. It doesn't just bulk. It actually is like a wrap going in and out. We saw this in the computer, and then we saw that the inquiry actually has written evidence where people who saw the bulkhead before the sinking had that type of deformation, which is actually new evidence that actually probably the fire doesn't explain the sinking, though. It explains the time of the sinking and why the Titanic, instead of being afloat for a really long time, it actually went very quickly with, unfortunately, a lot of people inside who had not had time to evacuate into the middle of the sea. With this, I'm going to finish just to highlight, to remind you that fire is an ancient hazard, has been facing humanity since we were a species, and is expected to morph into different hazards as the civilization actually continues. It's not expected to disappear. That fire engineers and the authorities and the fire service have been here since the dawn of civilization to protect us, sometimes more successful, sometimes less successful, depends on which country you go, the history is better or worse, and protecting people, protecting our property, and protecting the environment. It's a new ethos that goes into the realm of the fire engineer, which is not just humanity. Now you have to protect the planet to become sustainable. That I bet it, obviously, I'm going to claim this as a fire scientist, that if we have a better understanding of how fire ignites, spreads, emits, and suppresses, we definitely will go, and we are going to accelerate innovation, and we make the environment safer, both in the buildings and in the forest. And that fire is a very complex phenomena. They say that actually, scientists say that fire is as complex as the human body. So there are millions of doctors on the planet that are studying the human body, and we are only 2,000 scientists trying to understand on fire. So imagine how struggle it is that we go through as fire scientists. So any support from citizens will always be welcome. You giving us a remit, telling us the problems that you think we should be working on, you giving us recognition, saying this is actually really nice, and then let's let the rest to be done by authorities and industry, and hopefully the field of fire science can grow. Thank you very much.